Testing. Hello. Hi, everybody. My name is also Cameron. So apparently we are completely made of bosonic particles. So anyway, so thank you for having me back. Last year, I talked about the circumgalactic medium in the context of current generation of cosmological zoom-in simulations. And I argue that just like the clouds on the atmosphere of the Earth, the cloud in the galactic sky is tightly coupled with what's going on down here. In galactic scale, that means how we implement star formation and feedback. And these outflows are what producing the CGM in my last paper. And today, I want to focus on slightly more detailed of the CGM outflow in the more zoom-in, small scale simulation to simulate these outflow more realistically. Right. So the detailed questions that we are asking in this project is, right, what are the CGM outflows in the parsec scales that has been briefly mentioned by other people here? And what are the relevant physics that shape the CGM outflow? And basically the fundamental question is, in Halo, why is the CGM multi-phase? How is it multi-phase? So to do that, we run a set of AMR simulation with resolution down to 0.3 parsecs. So it's a very, very different scale here, but actually a custom art further developed by Alexei, who's a theorist at the University of Chicago in the supernova field. So I was fortunate enough to convince one of his students, Ian Remming, to do this project with me. Okay, so this is an obligatory, I would say, of multi-phase outflow of M82, right? So there is X-ray, optical, and the molecular all coincide more or less spatial location. So this is what motivated me to do this more realistically, right? In the background slide here, I have already a series of outflow snapshots of our simulation. Here we start with the what I call the adiabatic sim. That means just a normal hydro equation with no bells and whistles. And we systematically add new physics to the outflow and see what happens. So we have radiative cooling, thermal conduction, and finally the magnetic fields. And you can already tell that they are quite different, right? So the physics actually matters. All right, so this is, in this talk, I'm gonna show 3 simulations. The first one is with radiative cooling, and all the simulation have the same initial condition with some cloud that is turbulent-like structure with the dense area representing the coal or abundant of H1 or magnesium-2, and then you have the warm area that oxygen-6 traces, which is at the boundary of the cloud, right? So if I start the movie here, you see that the oxygen-6 are created by the stripping of the turbulent wake, and is actually very, very effective creating oxygen-6, and this might be able to explain the high carbon fraction that by Tomlinson et al. In the Castillo program in this starburst-driven wind. Also, let me play the movie again. Focus on the attention here. Cooling promotes thermal instability, and because of the wind interaction, it actually shatters into tiny, tiny clumps. And these are actually in sub-parsec scale or just a few parsec of very dense gas, right? And this, I'm also from this church of small clouds. Our leader here, Mike McCord, right? He showed that this simulation of cooling produces little tiny clumps everywhere in his simulation. But if you zoom in, re-simulate some patch, they don't have these fragments, right? And we want to basically propose this new paradigm shift that the CGM is not some big clump of 500 parsec or something like that. There's actually, I want to take this cloud analogy that I kind of did last year a little bit further, that say the CGM is actually a kind of a mist, and that made up tiny, tiny clumps. Right? So this is a picture of UC Santa Cruz just outside it. I would like to take a picture if there's a better picture, but I actually Googled this image. Anyway, so the next simulation I'm showing, the one with thermal conduction, also with cooling. when I play the movie, you can see the conduction front basically evaporate from outside in, right? But the coal gas in the inner core still cools, and the magnesium-2 abundance still increase. But eventually, within less than several mega years, the gas will fully evaporate. And this is problematic because in observation, we clearly see coal gas. So it's either that conductions are not operating, somehow the mean free path is too large, or that there is some other agent that prevents thermal conduction, right? So by this point, no more coal gas, right? Notice that the O6 is still very abundant at the tail of this, right? But the nature of thermal conduction is such that it smooths everything out. So the morphology is very different. Okay, finally, we want to add magnetic field to the simulation. We parameterize our simulation in the following way. So there's this beta inverse parameter. It's just the pressure of the magnetic field over the thermal pressure. And I just chose 0.1, and that corresponds to, in our simulation setup, the magnetic field about 2.6 microgauss. So this typical of galactic field, right? So you expect that they would just protect from thermal conduction, because you can only now conduct heat along the magnetic field line, but not perpendicular to it. So the conduction front still eats away some of the gas, but now the wind blowing from the left to right has wrapped the magnetic field around this coal gas, protecting it from evaporating. So this insulation is due to magnetic field draping around the cloud. And again, oxygen-6 is still very abundant. All right, so I just dig in the literature and see this is, everyone show X-ray, optical, or whatever phase of the M82. There's actually a lot of magnetic field observation have been done on the M82 as well. And this is from 1994. There is some vertical field line going in that direction along the perpendicular to the disk. Okay, so here is a few snapshots of variation of magnetic fields in our simulation. So the first one is without magnetic field, right? And again, I want to emphasize that these structures are 0.1 parsec, right? In a cosmological zoom-in simulation, I wish everybody good luck resolving this, right? It's never going to happen, right? Even if the next next generation is not going to happen. And the correct way to do this forward, and this is something I've been working on along with this project, is to do subgrid model. You have to have a subgrid model, just like star formation. And I think the field in the CGM will move in that direction. Anyway, so with the magnetic field here, I have weak field, a strong field, and strong field with conduction, right? The basic point is that as long as the magnetic field, the coal gas can survive. Right? Morphology might change a little bit based on the details of it. So I'm going to zoom in to 3 patches, all of these patches, and so in a 50 parsec region. So which row is one simulation? 2.6 microgauss, 26 microgauss, and then with conduction, right? The gas is very dense, about 1 per cc, and then due to cooling, everything is in the core of this is 10 to the 4 Kelvin, and the environment is 10 to the 4, right? How does it survive if you have conduction or other instabilities? So I started with 0.1 of this parameter. You can see at some late time, due to draping around the boundary here, the magnetic field has amplified by a factor of 100 or 1,000, right? So what that means is, as long as you have magnetic field in the halo, and which you have shown that there is, right? It can be very weak, microgauss or whatever. The mean field can be very small, but the fluctuation can be huge, and that is enough to protect your coal gas in the halo, right? So I would just summarize that we might be entering a paradigm shift, that the CGM is made of mist, not a gigantic clump. And then if you have thermal conduction, it may be completely evaporate, right? So we need some magnetic field in the halo, which we do to protect the coal gas. All right, thanks. Hi, Cameron. Yes, I'm actively working on that. The answer, I don't have an exact number, but I did rough calculation. You only need about, so this clouds I set up is about initially 50 50 parsec wide, right? But for integrated column, the size of a view radius, you don't need that many clouds to actually get the integrated column density of 0.6, for example. And the Hamming fraction is very high in this. So you basically in star forming galaxy, you hit oxygen 6 every single time. That's something I don't know because in our cooling function, we only have it down to 10 to the 4. We don't include molecular formation in the model. It's something to worth going into. However, I would say it's difficult to say because these clouds are small, so they are not self-shielded. So it's difficult to form molecular gas or dust. They will be just destroyed. That's my thought on that. We don't. The scale is small enough. The self-guide doesn't matter. Right, so the initial geometry of the field is parallel to the wind horizontally, and that is the weakest configuration we can set it up. Yeah, if you make it perpendicular to the wind, that the dripping becomes even more effective, right? So we want to just put a conservative way to do this, yeah. Yes. Right. So my McCourt and collaborators have gone to do radiative transfer kind of for Lyman alpha emission for the double peak that you have, and that constrain the number of clumps per volume that you need. And I will look into that paper. It's max clump or something. You need a high number. You can parameterize that by a clumping factor, and clumping factor is very, very high, at least 1 million.